Hi, in this video I'll be looking at Casella Berger Statistical Inference Chapter 1 and Problem 1. Right. So here the first question is, for each of the following experiments describe the sample space. We have to describe the sample space. Before that we should know what is sample space. Sample space is normally denoted by a capital letter S, and it is the all possible outcomes of a random experiment. Okay, now the first random experiment that we are interested in is tossing a coin 4 times. Okay, right. So we look at the first toss, right? So this is either it can be head or tail. Either it can be head or tail, right? Then you're going to pick the coin again and you are going to do the second toss. Okay, right. Let's say the first outcome of the first coin toss was head, then you would have the second coin toss. Either it can be head or tail. Same here, either it can be head or tail. Right. Then we are going to go to the second coin toss, right? So here again the possibilities are head, tail, head, tail, head, tail, head, and tail. Right. Then we are going to do it one last time because you're tossing the same coin 4 times, right? So this is head, tail, head, tail, head, tail, head, tail, head, tail, head, tail. It's a lot of heads and tosses. Head, tail, and head, tail. Right. So this is the whole random experiment. Now to write the sample space. Sample space means all possible outcomes. Let's see what are the all possible outcomes. So the first possible outcome would be, from the first coin toss you get a head, from the second coin toss you get a head, from the third coin toss head and head, right? So one possible outcome would be head, 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 right? Let's look at the next one. It would be, you can get a head from the first one, head from the second one, head from the third one, but in the fourth one you would get a tail. So this would be head, 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 tail, right? Likewise, the next possible option would be head, head, tail, head, 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 tail, head. Next one, head, head, tail, tail. Next one, head, tail, head, head. Right, now I'm in this branch. Okay, right. Next, head, tail, head, tail. Next one, head, tail, tail, head, head, tail, tail, tail. Right. So now I'm done with all these things. Now I'm done with this branch. Okay, I'm done. Right. Next, now I'll start from here. It can be tail, head, head, head. Okay, so I'll start writing down the possible outcomes in that branch. It would be head, head, starting with tail, tail, head, head, head. Right. The next one, tail, head, head, tail, tail, head, tail, head, tail, head, tail, tail. Right. So now I'm done with this branch. Next, only remaining one is the final one. Right. So it would be tail, tail, head, head, tail, tail, head, tail, 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 head, and finally tail, 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 tail. If I did this correctly, I tossed like for each coin toss there are only two possible outcomes, and I did it 4 times. So number of possible outcomes should be 16. Let's say whether there are 16 outcomes. Right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right. So I have done that correctly. So these are all possible 16 outcomes of tossing a coin 4 times. We go to the next experiment. Next experiment is count the number of insects in a damaged insect damage leaves on a plant. Okay, right. So that means you have, like, let's say there's a leaf like this, right? There's a leaf like this. Count the number of insect damage leaves on a plant, right? So let's say this is the plant, right? And now the random experiment is counting the number of leaves that were damaged by insects, right? So let's say this is sample space, right? So it is count the number, right? So you have to count the number of leaves damaged by the insects. Let's say you observe a plant, and let's say all the leaves are healthy. This one is good, this one is good, this one is good, this one is good. So it can be 0, right? Next possible number for this random experiment is there cannot be 0.5 damaged leaves. There cannot be 0.05 damaged leaves. No, right? The next possible number that my random experiment can take is 1, right? It can be 1 damaged leaf, right? Maybe there are some insect bites like this. Okay, maybe 2 are damaged, right? 2. Likewise, it can go on forever. So this is sample space would be the whole numbers including 0. This is the sample space for this particular random experiment. Right. Next one. Right. We look at the next random experiment. Measure the lifetime in hours of a particular brand of light bulb. Right. So you have the light bulb like this. Right. This is your light bulb, and right, it is giving you light. Okay. So the random variable you are measuring is lifetime in hours. So you are observing this bulb and you are trying to figure out what is the lifetime. So sample space. So time, right? We are measuring time. Time, can it be negative 5.6 seconds? No, right? Since we are considering a time, lifetime of the light bulb cannot be negative. Okay, right? Like, can it be negative 0.001? No, still no, right? Can it be 0? Yes, it is possible, right? Let's say whatever the brand new light bulb you got, it was a broken one, right? So it can be 0, right? Can it be 0.00001 seconds? Yes. Can it be 0.0000001 seconds? Yes. Can it take like 10 seconds? Yes. Can it take 1000 seconds? Yes. So it can be any number greater than 0. So this can be t can be any number greater than or equal to 0. That is your sample space. Okay, right? Because the random variable you are measuring can take any value greater than 0. Right. Next one. Record the weight of 10-day-old lab rats. Right. So you have rats like this. They have a tail, maybe ears and stuff. Right. Okay. So you are going to put him on a scale, and this is the scale, and measure the weight, right? So this is, let's say, weight of a 10-day-old rat, right? Again, so what are the values this random variable can take, right? My x can take any value greater than or equal to 0, right? Why? Can the weight of rat be negative 0.5 grams? No, right? Can it be negative 0.0001 grams? No, right? Can it be 0 grams? Still no, right? Like, there must be some way. So we cannot include this greater than or equal to sign. It weight must be greater than 0, right? So can it be 0.001 grams? Yes. Can it be 10 grams? Yes. Can it be 100 grams? Yes. We don't know, like, we don't know any upper limit, so we'll just leave it as sample space would be any number greater than 0, right? Like, it's important that equal sign is not included here, right? Then the final experiment is observe the proportion of defective in a shipment of electronic components, right? So here we are looking at a collection of shipments. Okay, right? Let's say observe the right. So this is, so how do we do this? Right. This is a proportion. Now how do you take a proportion? Let's say this is the observe the proportion defectives in a shipment of electronic items, right? So if you look at the electronic items, let's say these are the electronic items. Okay, these are the electronic items, right? Let's say there are, for an example, let's say there are 10, and the defective ones, I'll mark it with this purple or pink, let's say, right, 3. Okay, let's say 3 are defective, right? So in this particular example, the proportion would be, let's say p hat, like proportion would be number of defective items, 3 are defective, and total there are 10. Okay, 1 2 3 4 5 6 7 8 9, okay, right? Yeah, there are 10 now. Okay, so the proportion of defective is 10, right? There can be a scenario where none are defective, right? So the, if none of them are defective, 1 2 3 4 5 6 7 8 9 10, right? So if none are defective, proportion would be 0 over 10, right? Okay, so the sample space would be, let's take a general example. Let's say there are n items, right? So these are the electronic items, right? So the sample space would be, first one, either it can be 0 over n, the proportion can be 0 defective items, or it can be 1 defective item, or it can be 2 defective items, right? So what would be the maximum defective items here, right? Like, let's go back to our initial example. This can be defective, this can be defective, this can be defective, likewise all these things can be defective, right? So for this particular example, p hat would be 10 over 10, right? Similarly, if you generalize it for the n case, when there are n items, let's say all the n items are defective, then the proportion would be n over n. Okay, right? So if you simplify this, this is starting one is 0, 1 over n, 2 over n, up to 1. This is your sample space, or in other words, all possible outcomes of the random variable, right? Thank you guys.